Have you ever just stopped and wondered how a massive, complex game, with literally thousands of things happening all at once, can run so smoothly, frame after frame, without just collapsing under its own weight? Well, it's not magic. It's a masterpiece of engineering. And today, we're going to dive deep into the V-Engine's architecture to see exactly how it conducts this incredible symphony of systems.
So let's get right into it, because this is the central question, right? Every 16 milliseconds, that's a 60th of a second, the engine is juggling an absolutely immense amount of work. The secret isn't just about raw speed. It's about doing things smart, with a really deep understanding of the hardware it's running on.
See, here's the thing. V-Engine doesn't just use your computer's threads, it fundamentally understands its CPU topology. To build something truly stable, you have to start right from the metal, from the silicon itself.
Okay, to really get this, we've got to talk about something called simultaneous multi-threading, or SMT. A modern CPU, like this Intel i7, might have 8 physical cores. But thanks to SMT, each of those cores can pretend to be 2 logical cores, giving you 16 threads in total. Now the key word there is pretend. They're not truly independent. They have to share critical resources, like the superfast L1 and L2 cache. Think of it like 2 chefs trying to work on the same tiny cutting board. They're bound to get in each other's way, and that can cause little delays.
And this is where V-Engine gets really clever. It doesn't treat all threads the same. For something like rendering, where you just need raw number crunching power, we go into throughput mode and saturate all 16 logical threads. But for jobs that are super sensitive to delays, like AI decision-making, using those shared logical threads can cause problems. It's called cache contention. Those 2 logical threads are fighting over the same workspace, slowing each other down just a tiny bit. So for those critical tasks, we switch to a dedicated latency mode.
So here's the secret weapon. V-Engine uses a technique called Thread Affinity. It literally pins those sensitive jobs to the 8 physical cores, completely avoiding that SMT overhead. This guarantees that a job's data stays warm and ready in the cache, which gives you rock-solid, predictable performance. This hardware awareness isn't just a minor optimization, it's the absolute bedrock of the engine's stability.
Okay, so we've solved the where. We know which cores to use for which jobs to guarantee stability. But the next, equally important challenge is deciding when these jobs should run. This is where the engine puts on its conductor's hat and starts directing the flow of work. You've probably seen this in games before. You're running around, everything is silky smooth, and then bam, a massive stutter out of nowhere. That's often what we call the thundering herd effect. It's what happens when you have, say, 100 AI characters all deciding to recalculate their complex paths at the exact same instant. The result is a huge CPU spike and a jarring drop in your frame rate that just shatters the illusion. The engine avoids this stampede with a really elegant strategy called declarative scheduling. Instead of just letting everything fire at once, developers define patterns for how jobs should run. For instance, using every n frames of 5, we can stagger that heavy AI pathfinding so only a fifth of the agents update each frame, smoothing out the load. And for non-critical work, like decompressing an asset in the background, the WhenIdle constraint is brilliant. It tells the engine, hey, only run this job when you have spare cycles, which keeps the frame time perfectly flat.
So we've got jobs running on the right cores at the right time. But they don't operate in a vacuum, right? They need to talk to each other, to share their results. And that brings up the next big architectural challenge. How do you let them communicate without creating new bottlenecks and making one system wait for another? This quote from the design docs just says it all, really. Everything is designed to be asynchronous and non-blocking. Now that's just a technical way of saying that no system is ever forced to stop and wait for another one. A system can fire off a request for some complex work and then immediately move on to its next task, trusting that it'll get a notification when the result is ready.
And this is achieved with what's called the event-to-job pipeline. It's a beautiful flow. Let's walk through it. Say a simple event happens, like a collision. This doesn't stop the game. Instead, it just dispatches a parallel job to some worker threads to handle all the heavy physics math. Once that job is done, it doesn't interrupt anything either. It simply queues up a new result event, like play a sound, which the main system will pick up and process in a future frame. It's a gorgeous, elegant flow that keeps the entire engine feeling responsive.
Now, you'd think this intense focus on architecture might stop with the core engine, but nope. It extends all the way to the developer tools. Because let's be honest, if the tools you're using to debug the game can crash it, they're not very helpful. V-Engine applies these same principles of separation and stability to its own control room.
the developer console.
The console isn't just one big program. It's a really smart 3-layer sandbox. At the top, you have the VTerm system. That's just the front end, the UI that a developer actually types into. Below that, commands get sent to the kernel system, which acts like a secure router. It checks permissions and validates everything. And only if a command is approved and needs to talk to the operating system does it get passed to the final layer, the host system. This is a totally sandboxed backend that provides safe, asynchronous OS access, completely walled off from the main engine.
And here's why that's so brilliant. This separation means a developer can run powerful system commands right from the engine, like listing files or executing a script, with basically zero risk of blocking or crashing the main game loop. It's about building in stability, not just for the player, but for the developer too.
All right, let's pull all of this together. When you look at these different pieces, you can see they're not just a random collection of features. They form 4 distinct pillars, the V-engine's entire blueprint for stability.
First, there's hardware-aware concurrency, which respects the CPU's actual design. Second, staggered scheduling, which acts as a conductor to prevent those jarring CPU spikes. Third, asynchronous pipelines, allowing all the systems to communicate without ever waiting. And finally, secure kernel tooling, which protects the engine even during the chaos of development. Each pillar builds directly on the last.
And there you have it. By combining deep hardware awareness with smart scheduling, asynchronous communication, and sandboxed tooling, V-Engine creates a true symphony of systems that stays stable even under the most extreme loads. You've now finished the architecture deep dives. Up next, we actually start implementing the engine from scratch.
And that kind of leaves us with one big question, doesn't it? We've looked at all this through the lens of a game engine, but the problems of concurrency, scheduling, and stability aren't unique to games. As software everywhere gets more complex and more parallel, you have to wonder, is this deep, multi-layered approach to system orchestration the new blueprint for building any resilient, real-time application?